Hello everyone, welcome to robotics module. Today we are going to discuss forward kinematics using DH parameters. Here is the outline. First we'll have a recap on what we studied last time. The main topic for today is forward kinematics. So we will do forward kinematics for 2-link planar manipulator, 3-link cylindrical robot, and finally for the spherical wrist. Last time we presented a convention to name the joints and links of a given manipulator. So the joints are numbered starting from 1, whereas the links are numbered starting from 0. Next, the Denavit-Hartenberg convention or the DH convention was introduced. So if we are to follow this convention, two constraints had to be satisfied. The first constraint was axis xi should be perpendicular to axis zi minus 1. The second constraint was axis xi should intersect axis zi minus 1. Once these two constraints are satisfied, we could obtain a transformation matrix between two neighboring links, and we called it as the AI matrix. So AI matrix would give the transformation between I minus 1 frame to frame I. Now we could observe the same setup from a different viewpoint where the transformation could be given by 4 successive basic transformations. So we rotate about z-axis theta angle followed by a translation on z-axis d amount, and next we have a translation on x-axis a amount, and finally a rotation about x-axis alpha amount. Finally, frame assignment steps were presented. So in this lecture, we will use these steps to assign frames to a given manipulator. First, we will look at a further simplification of the notation. In the DH convention, the only variable angle we have to deal with is theta, which is the joint angle. All the remaining parameters would be either constant angles or else distances. So let's simplify the notation further. So if we have cos theta I, previously we used c theta I, and now we are going to use just ci. Okay. For example, let's take cos theta 4. So that's c theta 4 previously. Now it's going to be just c4. And we can also consider cos theta I plus theta j. And previously it was c theta I plus theta j. And now we will just use Cij. For example, if we have cos theta 1 plus theta 2, then this is going to be c theta 1 plus theta 2, but now it's going to be just c1 2. Okay. So the first manipulator we are going to look at is the 2-link planar manipulator. Now you might be wondering why it is called a 2-link manipulator when we can observe 3 links. Well, that has been the case in practice because the 0th link is attached to the environment and it cannot actually move. So we most often refer to this manipulator as a 2-link manipulator. And it is called a planar manipulator because it can only move on the planar surface on this presentation slide. In the 2-link planar manipulator, we have link 0 here, link 1 and link 2, okay, as well as joint 1 and joint 2. Now we are going to use the steps that we learned last time to assign the coordinate frames to this manipulator. So step 1, establish Zi. So you already know from last lecture that we will assign all the Z axes to the joint actuation directions. Now both these joint axes, that is J1 here and J2 there, are perpendicular to this presentation slide. Okay, so you can either assign the Z axis going into the slide or coming out of the slide. But since we are measuring the joint angle counterclockwise, we will assign Z axis as coming out of this presentation slide. Okay, so we will just mention that because we are unable to portray that in this slide. So we will say that Z0 is normal to plane, and we have Z1 also normal to plane. Okay. Step 2, base frame. We can start by choosing the origin of the base frame, and the origin O0 can be anywhere along the Z0 axis. Okay, but the natural choice should be the point where Z0 axis intersects this page. So we will mark O0 here. Understood? So now we have Z0 and O0, the origin, and we are going to choose X0. The choice of X0 is totally up to you, but there are certain natural selections we often use. So maybe how about we choose X0 in this direction. Okay. Y0 axis should form a right-handed set with X0 and Z0. So we can draw the Y0 axis vertically upward like this. So with that, the base frame or the zeroth frame is complete. Step 3, X1 and O1. Now step 3 is a recursive process that we will perform until the end effector frame. So there are 3 cases that can happen, and in the 2-link planar manipulator what we have here is the case where Z0 and Z1 are parallel to each other. So there can be infinitely many common normals between Z0 and Z1, but we are going to choose the one that goes through O0, and we will assign X1 along that common norm. So we take this common normal which is on the slide, and this is going to be our X1 axis. Okay. So the origin of frame 1 will be at the intersection of X1 and Z1. So we will have O1 here. Okay. Again, Y1 should form a right-handed set with X1 and Z1. Therefore, we will have Y1 in this direction. Okay. So with that, frame number 1 is also complete. Step 4, end effector frame, which is frame number 2. So you have the freedom to choose the end effector frame, and that will depend on your requirements. Since we don't have any requirement at this moment, let's just choose the end of link 2 and place the frame 2 like this. Okay. Now it is time to go back to the DH convention, and we are going to fill a table known as the DH table for this manipulator. So there are 4 parameters for each transformation matrix, and that would go in a single row of this table. We start filling up the table from link 1, so that is I equals 1. Okay, so we start with 1. So first we have A1. So it says in this definition, A is the distance between axis Z0 and Z1 measured along axis x1. So we are talking about this distance, and here it is A1, a constant value, right? So we can put A1 here. Next we have alpha 1. So alpha is the angle between axis Z0 and Z1 measured about x1. Now we know that Z0 and Z1 are parallel, therefore the angle between those two will be 0. So we can put 0 here. Okay. Next we have D1. So from the definition we have distance from O0. So O0 is here, so this point, to the intersection of x1 and Z0. So x1 is this, and Z0 comes out of this slide. So the intersection would be the same point, right? Therefore the distance between those 2 points is again 0. Okay. Next it would be theta 1. So theta is the angle between x0 and x1 about Z0. So here we have x0, here we have x1. So we need the angle between these two measured about Z0 with the positive sense. Therefore this is going to be theta 1. Now this is a joint, therefore this theta 1 is a variable. So we can put theta 1, and we are going to put an asterisk as well, which says that it is a variable. Okay. So I hope you understood how we filled out the first row of the DH table, and now we are going to repeat the same thing. So we go to link 2. Okay. Next we need A2, that is the distance between Z1 and Z2 measured along x2, right? So here we have Z1 and here we have Z2. So the distance between these two, here we have A2, right? Again, that is a constant value which we call as the link length. So we can put that as A2 here. Okay. Next we need alpha 2. So alpha is the angle between Z1 and Z2. Again, Z1 and Z2 are parallel, therefore the angle would be 0. So we can put 0 here. Then we need D2. So D is distance from O1. So here we have O1. And we need to find the intersection of x2 and Z1. So this is x2 and intersection with Z1. So it is again the same point. Therefore the distance is going to be 0. Okay. And finally we need theta 2. So it is the angle between x1 and x2 about Z1. So here we have x1, x2 and measured about Z1, and that angle is theta 2 here, right? So theta 2 is also a variable because of the second joint. So we can put theta 2 here and an asterisk. Okay, so with that we have completed the DH table for the two-link planar manipulator. I hope you understood. Next, we are going to find the A matrices by looking at the DH table. So the A matrix has the following form that we derived last time. So it is all about just substituting these values in the DH table to find all the A matrices that we require to do forward kinematics. We will start with A1, which is the homogeneous transformation matrix from 0th frame to 1st frame. So let me write A1. So the first entry is cos theta. So we have theta 1 in the first row of the DH table, and using the simplified notation, now we can write that as C1. Okay, and similarly sin theta is going to be S1, and we have two zeros here. We go to the second column. So we have cos alpha. Alpha is equal to 0 in the first row of the DH table. Therefore, this is going to be minus S1. And cos theta cos alpha is going to be cos theta, because cos alpha is 1. So this is going to be C1. Then we have sin alpha 1. Alpha 1 is 0. Therefore, this is going to be 0. And this is also 0. Okay, so third column, sin theta sin alpha. So sin alpha is going to be 0. So this is 0. Then we have cos theta sin alpha. Again, this is going to be 0. And cos alpha, alpha 1 is equal to 0. Therefore, this is 1. And this is 0. Okay. Final column, we have A cos theta. So that is going to be A1 C1. Okay. Then A sin theta. So we have A1 sin. So we are using the values from the first row of the DH table. So D1 is 0. And finally we have a 1 here. So this is the A1 matrix. Okay. And similarly, we can find A2 matrix. So we just look at the second row of the DH table and we can substitute for the A2 matrix. So we get C2 S2 0 0, and next one is going to be minus S2 C2. Alpha 2 is also 0, therefore this is 0 and this is also 0. Third column, we have sin alpha term where alpha equals 0, therefore it is 0. This is also 0. Cos alpha where alpha is 0, therefore this is going to be 1 and this is 0. The final column, A2 C2, right? And this is A2 S2, D2 equals 0, and finally we have a 1. So there we have the A2 matrix. Okay. Now we can find the transformation matrices, the T matrices, or we can call them as H matrices as well. So what is T01? Yes. So it's nothing but the A1 matrix, right? The transformation matrix from coordinate frame 0 to frame 1. Then what about T02? So that is going to be the multiplication of A1 and A2, right? So we have all the A matrices ready, so it's just the multiplication that we need to do. So the end effector frame, that is T02 in this case, can be obtained by multiplying A1 and A2, and we will get this resulting matrix. Right? Now, if you can remember, in the introductory lecture, we did this same thing using first principles, that is also for a two-link planar manipulator, and here we have the same answer using the DH table. And this point, the X and Y point, is this origin of the second frame. Okay. Okay. The second manipulator we are going to look at is the 3-link cylindrical robot. And just similar to the previous case, you will find there are 4 links including the base link, but we refer to this as a 3-link cylindrical robot. Okay. In the 3-link cylindrical manipulator, we have link 0, let's say somewhere here. Then we have link 1, link 2 and link 3, as well as joint 1, joint 2 and joint 3. Okay. And the step 1 is to establish ZIs. So we will assign all the Z axes to the joint actuation directions. Okay. So for the joint 1, the actuation direction would be vertically upwards. Therefore, we will assign Z node like this, and assuming that this is our positive direction. Okay. Next, for the joint 2, it is a prismatic joint that moves up and down. So again, we can assign Z1 like this. Okay. Third joint is also a prismatic joint moving left to right. So I'm going to assign Z2 in this direction. Okay. So all the Z axes have been assigned. Step 2, the base frame. We can start by choosing the origin of the base frame, and the origin O0 can be anywhere along the Z node axis. But the natural choice should be the point where Z node axis intersects the ground surface. So we will mark O0 here. Okay. So now we have Z0 and O0, and we are going to choose X0. The choice of X0 is totally up to you. And for a change, how about we choose X0 in this direction where it comes out of the slide. Okay. Y0 should form a right-handed set. Therefore, Y0 should be in this direction. Okay. Step 3, X1 and O1. Out of the 3 cases that can happen, what we have here is a special case where Z node and Z1 are basically the same axis. So there can be many choices for X1 perpendicular to Z node and Z1. Okay. So one such choice of X1 should be the one that goes through O0, similar to the previous example we did. But then our frame 1 is going to coincide with frame 0. So there is no point doing like that. So another option is to choose X1 going through joint 2 like this. And I have chosen it to be parallel with X0 because when I do that, it will be convenient for me at the DH table. What you have to remember is that if the 2 DH constraints are satisfied, you cannot be wrong with your frame assignment. So the origin of frame 1 should obviously be at the intersection of Z1 and X1. So I can put O1 here. Okay. Next, Y1 should form a right-handed set. Therefore, Y1 should be in this direction. Step 3 continues for X2 and O2. So out of the 3 cases, what we have here is the case where Z1 and Z2 intersects. In that case, we choose X2 normal to the plane formed by Z1 and Z2, and it goes through the intersecting point. So you can either choose x2 coming out of the presentation slide or going into the presentation slide. But we will choose x2 having the same direction as x1 for our convenience at DH table. So I have x2 in this direction. Okay. And we are going to place the origin of frame 2 at the intersection of Z1 and Z2. So we have it here. Okay. Y2 should form a right-handed set. Therefore, Y2 should be in this direction. Okay. Finally, we need to assign the end effector frame, which is frame number 3. And I'm going to assign frame 3 with the same orientation of frame number 2, so that it will be easier for us when we do the DH table. Okay, so we will have x3 in this direction, z3 in this direction, and y3 in this direction, where this is O3. Okay, now we are ready to fill the DH table. We start with link 1. So A1 is the distance between Z0 and Z1. So that is going to be 0 because Z0 and Z1 are basically the same axes. Alpha 1 is the angle between Z0 and Z1, and that is also 0. D1 is the distance from O0 to the intersection of x1 and Z0. So x1 is here, Z0 is there, so that intersecting point is here, and O0 is here. So this is the distance we are talking about. So let's take that as D1. Okay, and it is a constant. Next we have theta 1. So theta 1 is the angle between x0 and x1. So in this case we have a revolute joint here, so that theta angle is therefore a variable, right? So we can write theta 1, and we are going to put an asterisk because it's a variable. Okay, so first row is complete. Now we'll move on to the second row. So that is regarding link 2. So A2 is distance between Z1 and Z2. So you can see here Z1 and Z2 are intersecting. Therefore, the distance between those two is 0. Next we have alpha 2. So alpha is the angle between Z1 and Z2 measured about x2. So we have x2 here and Z1 there, and this is Z2. Now you have to be careful in this case because this is the positive sense of the angle about x2, right? And here we have Z1 and you have Z2 here. So from Z1 to Z2 we should be measuring the angle clockwise, but positive sense is counterclockwise. Therefore the angle should be minus 90 degrees. Okay, so I hope you understood that part. Next we have D2. So D2 is from O1. So we have O1 here to the intersection of x2 and Z1. x2 and Z1. So the intersecting point is here. O1 is here. So we are talking about this distance. But since we have a prismatic joint, that distance is going to be a variable. Okay, so we can put D2 and an asterisk. Okay, next we have theta 2, so that is the angle between x1 and x2 about z1 axis. So we have x1 this direction and x2 that direction. So those two directions are going to be same because the joints are prismatic, therefore the angle between those two is going to be 0. Okay, so that's why we chose x2 to be in the same direction as x1. Finally, we come to link 3 and let's see what we have for A3. So A3 is the distance between Z2 and Z3. So you can see Z2 and Z3 basically are the same axis, right? Therefore, the distance between those two will be 0. Okay. Next, we have alpha 3. So that is the angle between Z2 and Z3. So that's also 0 because they are the same axes. Okay. Next, we have D3. So D3 is the distance from O2. So O2 is here, and the intersection of x3. So x3 is here, and Z2. So that the point is here, O3. So we are talking about this distance. Okay. And again, we have a prismatic joint here. Therefore, we are having D3, which is a variable, right? So we can write D3 star. Okay. And finally, we have theta 3. So theta 3 is the angle between x2 and x3. So you can see x2 and x3 are in the same direction, and that direction won't change because this joint is prismatic. Therefore, the angle between those two axes are 0. Alright, so we have finished the DH table for the 3-link cylindrical manipulator. Now we are able to generate the A matrices. So from the first row of DH table, we can write the A1 matrix. So we have cos theta 1, that is C1, sin theta 1 is S1, 0, 0. Second column we have minus S theta 1 and cos 0, therefore we have S minus S1, and we have C1, sin 0 is 0 and another 0 here. Third column we have sin alpha is 0, therefore this is going to be 0, and this is also 0. Cos alpha is 1 and 0, and the final column would be A is 0, therefore both these would be 0, and D is equal to D1, and finally we have a 1. So this is our A1 matrix. Next we go to the second row of the DH table and we can generate A2 from that. So we would have cos theta would be 1 because theta 2 equals 0. Sin theta would be 0 and 2 zeros here. Second column we have sin theta, therefore it's going to be 0. Next we have cos 0 and cos minus 90, so that is also 0. Sin minus 90 would be minus 1 and 0. Next we have third column. So sine 0 is 0. Then we have minus cos 0 and sine minus 90. So that's going to be a plus 1. And cos minus 90 would be 0, another 0. And the final column is, again the a's are 0, therefore these two will be 0. D is D2 and a 1. Okay, so that is our A2 matrix. And finally, by looking at the third row of the DH table, we can generate A3. So we have cos 0 is 1, sine 0 is 0, and two more zeros here. Second column, minus sine 0 is 0. Then we have cos 0 and another cos 0, that's going to be 1. Sine 0 would be 0 and another 0 here. Third column we have sine 0, therefore it's 0 and another 0 here. Cos 0 is 1 and finally we have a 0 again. The final column, these two will be 0 because A is equal 0. D is going to be D3 and finally we have a 1. Now A3 could have been obtained by looking at the coordinate frames as well. So if the coordinate frames throughout the manipulator have easier representations relative to each other, we can actually obtain the transformation matrices just by looking at the frame assignment. But sometimes it's going to be difficult. That's why we would use the DH table. Okay. Now we can write the T matrices. So for T01, that is equal to A1. So what is T02? That would be equal to the multiplication of A1 and A2. And finally, T03, which is the frame for the end effector, so that we can obtain by multiplying A1, A2 and A3. Okay. So the end effector frame would be T03 and you will get the following result. You can check that. The final example we are going to look at is a part of the manipulator and it is called the spherical wrist, which is a special arrangement. A spherical wrist has 3 revolute joints and the 3 joint axes intersect at a common point. Here it is drawn with exaggeration, but all these 3 joints can be inside a single unit. So we can have a manipulator with 3 joints and at the end we can attach a spherical wrist. That is, let's say we have manipulator with 3 joints, okay, and here now I can attach this spherical wrist. Okay, the special thing about the spherical wrist is that it can achieve any orientation without changing its origin or that common point of intersection here. Kinematic analysis of manipulators can be greatly simplified if there is a spherical wrist because we can decouple position and orientation of the end effector. So for now, we will look at the forward kinematic aspect of the spherical wrist. but later we will revisit this arrangement when we study about inverse kinematics. We will start frame assignment by z-axis. So z-axis would be chosen as the joint actuation direction. Therefore, I would have z0 in this direction, and here I will have z1 downward with the positive sense of theta 2, and next I have z2 in this direction. Okay, so next I am going to choose O0. Now by looking at this arrangement, O0 can be anywhere on the Z0 axis, and a good choice would be this point, right? O0. Okay, now we have to choose X0. So you can choose any direction which is perpendicular to Z0, and let me choose Z0 that is coming out of this presentation slide. So this is going to be my X0. So the base frame is done. We don't have to worry about Y0 because it is implicit here. Okay, so the next thing we have to do is find what case this is. So this is the intersection of Z0 and Z1. Therefore, X1 will be either coming out of this slide or going into the slide. So since X0 is coming out of this slide, let me choose X1 also coming out of this slide. Okay. So frame 1 is also done, and O1 would be that same intersection point. Alright, next, if we look at Z1 and Z2, they are again intersecting at that common point. Therefore, X2 would be also coming out of the slide or going into the slide at that intersection point, and I'm going to choose X2 similar to X0 and X1. So I have X2 here, right? And therefore O2 will be at same intersection point. Alright, and finally, if you look at the end effector, we can choose Z3 same as Z2. So this is Z3, and that can be the approach direction A. Okay, let's fill the DH table now. So if you take all three links, 1, 2 and 3, you will find the link length A will be 0 for all these three, because A means the distance between the z-axes, and here all z-axes intersect at that common point. Okay, so alpha is the angle between the z-axes. So alpha 1 is the angle between Z0 and Z1. So we have Z0 here, Z1 there. So the angle should be 90 degrees. So we have to check whether that is plus 90 or minus 90. Now X1 axis is in this direction. Therefore, this angle is going to be minus 90. Okay, considering the positive sense. Next, we want to find the angle between Z2 and Z1. So here we have Z2 and Z1. Again, that's 90 degrees. But in this case, we are going to measure the angle about X2. The positive sense is counterclockwise. So this is counterclockwise. So that's going to be a positive 90. Okay, and finally the angle between Z2 and Z3, so they are basically the same axis, so that's going to be 0 here, and the D values So if you look at this figure, for the first two cases it's going to be 0 because the intersection points and the origins are the same point. But for the final one, let me take this point to be O3 and let me take this distance to be D3. Okay, so the distance between O2 and the intersection point of X3 and Z2 is O3, therefore this distance would be D3, and that is a constant as well. Finally, the theta column, so all these are 3 revolute joints, so that would give us theta 1 star, theta 2 star and theta 3 star. Okay, so if you work out the A matrices, you will get the following matrices from the DH table: A1, A2 and A3. We can find the end effector transformation matrix, and that is going to be T03. So this is equal to A1 times A2 times A3. So this would give us a rotation matrix R03 and a translation T03 and 1. Okay, if you work that out, you would get the following homogeneous transformation matrix. Now if you look closely, the rotation matrix part of this T matrix, which is this part, it should be a little familiar to you, and in fact it can be identified as Euler Z, Y, Z transformation with respect to frame 0. So you would have X here, Y there and Z there. Okay, with that we have come to the end of this lecture, and let me summarize what we studied. So first we looked at a 2-link planar manipulator and we derived the DH table, and using the DH table we obtained the end effector homogeneous transformation matrix. Next we looked at a 3-link cylindrical manipulator. Again we obtained the DH table, and from that we obtained the end effector homogeneous transformation matrix. Finally, we looked at something called a spherical wrist, which is a special arrangement, and in that there are 3 revolute joints which intersect at a common point. So the spherical wrist possesses the transformation of Z, Y, Z Euler angles. Now if you go through different textbooks, you will find that there can be slight variations of the parameters, and I want you to stick to the convention we studied in this module. Thank you very much.